Imagine a fully functioning spacecraft, roughly the size of a shoebox. It relies on an aerospace standard known as a CubeSat, and resting on a lab bench, it looks pretty unassuming. To get off Earth, this tiny box has to hitch a ride. It gets packed tightly inside a deployment pod and tucked away on a conventional launch vehicle, alongside much larger, heavier satellites. But once it reaches the vacuum of orbit, it executes a flawless mechanical trick. The box opens, and ultra-thin booms extend outward. In a matter of seconds, it unfolds a massive, highly reflective mylar sheet. This extreme transformation relies on precise aerospace engineering to turn a compact payload into a giant functional propulsion system. Packing something enormous into a package so small provides a precise structural foundation. Engineers use this folding design to bypass one of the most punishing physical roadblocks in deep space travel. For decades, moving anything through space required massive chemical explosions. Traditional rockets rely on igniting thousands of tons of volatile liquids just to get off the launch pad. That reliance on explosive chemistry locks engineers into a mathematical trap known as the rocket equation. This animated bar chart shows how total mass is distributed on a traditional spacecraft. If you want to travel to a distant target, you need more fuel, but fuel is incredibly heavy. As the fuel requirement grows to cover that distance, the space left over for actual science instruments shrinks to almost nothing. A massive, ultra-thin sail bypasses this math entirely. It solves the mass problem by completely eliminating internal chemical fuel. Because the source of propulsion is placed completely outside the spacecraft, engineers can dedicate the entire internal volume of that tiny shoebox to cameras, sensors, and mapping equipment. When people hear the term solar sail, it usually brings to mind the concept of wind. There is a common assumption that the spacecraft is pushed by the solar wind. The sun does eject streams of protons and electrons, but those particles are far too sparse to provide any meaningful thrust for a spacecraft. Instead, the sail relies on a physical mechanism called solar radiation pressure. It is propelled by light itself. This vector graphic illustrates a counterintuitive quirk of physics. Photons, the particles of light, have zero mass but possess measurable momentum. When billions of photons strike the highly reflective sail and bounce off, they transfer their momentum directly into the barrier, creating physical thrust. The actual force generated by this process is microscopic. The total pressure pushing against the sail feels roughly equal to the physical weight of a single piece of paper resting on your hand. While a force that faint is useless for lifting a rocket off a launch pad, it becomes the dominant engine for travel once a spacecraft is free from Earth's gravity. Deep space is a frictionless vacuum. There is no air resistance, no drag, and nothing to slow an object down. Because of that environment, the tiny push from the sun's photons doesn't just happen once. It continues every single second the mylar sheet is exposed to the light. This line chart compares accumulated thrust. A standard rocket gets a steep, immediate speed spike, but plateaus the instant fuel runs out. The solar sail experiences a slow, shallow curve. Over months and years, this continuous acceleration eventually overtakes the rocket's top speed. Time is the true engine of a solar sail. With an infinite supply of incoming light, a weak physical push compounds into an enormous velocity advantage. When a traditional satellite runs out of propellant, its mission ends. It becomes a dead, drifting brick. A solar sail is constantly being pushed, keeping it highly nimble. Engineers can angle the reflective sheet to steer. That constant, free thrust allows the sail to perform complex, dynamic orbital changes that would instantly drain a traditional rocket's limited fuel reserves. These continuous orbital gymnastics allow for an ambitious mission profile. A probe can traverse the solar system, adjust its trajectory, and smoothly intercept and match speeds with a distant minor moon or space rock. Because it never carries chemical tanks, the entirety of that tiny spacecraft arrives fully packed with the necessary scientific and mapping instruments. By capturing the momentum of the smallest, massless particles in the universe, engineers have turned a folded box of electronics into humanity's most efficient tool for hunting down massive cosmic bodies.